Okay, welcome to week one of ChemLab. So yes, I'm doing both Math Sci and ChemLab because I lead both events. Yay, joy. Anyways, so these are the example problems because I don't think we're going to have enough time to go over everything, go over the example problems because guess what? We only have 1 week, or sorry, 1 day per week to really go over these examples. So because of that, we're just going to focus on content during the actual lesson, but then these videos are here so that you guys have something as a reference for example problems. So let's just jump straight to it. So the first set of example problems I want to do, so once you get these slides, they'll be on slide 8, are the isotope practices. So let's just start with the very first isotope practice. How do I get rid of this? There it is. I'm getting much better at these notes app things. So oh my, what happened here? There it is. All right. So isotope practice. So then the very first one you might see might look like this, 238, 92, and then a question mark. Well, the goal of this is to figure out what is this question mark. And the way you do this is because if you remember the structure of how you represent these elements, this value represents the atomic number. And this is the, was it? A number of protons and the number of neutrons. And then when it comes to identifying what kind of element you have, oh, and also a side note, the atomic number is equivalent to the number of protons we have. So that means, and we also need to remember that the atomic number is unique to each element. So in other words, if we want to figure out what this question mark is, we got to figure out what this atomic number is. Well, is there a way I can like upload a periodic table here? No. Oh, whoops. I think I just deleted everything. That's unfortunate. Oh, no, I did not. Yeah, I don't think I can upload a periodic table, but that's okay. I'll just tell you the answer of what that 92 represents because if you were to look at the periodic table and look for the number 92, you'll see that 92 corresponds to you. Not you as in the person watching, but you as in the element. And this is shorthand for uranium. So that means uranium, is what this question mark is. That's the identity of this isotope. All right, so that's the first one down. Let's go on to the next one. So 235, 92, question mark. Well, what could this question mark be? Well, remember, it's the atomic number that really determines what the element that we have at hand. And it doesn't really matter what that top number is. We only care about this bottom number. And since we have 92 again, well, that means this is also uranium. The only difference is that if you look at the total amount of neutrons, well, the top uranium, uranium-238, has 3 more neutrons than the bottom uranium. And I know that because, well, we have 92 protons in both uraniums because that's what defines a uranium, 92 protons. So then that means because we have a difference of 238 and 235, that means the only thing that changed was the amount of neutrons. And if you take the difference between those, what was it? Those isotope the amount of protons and the amount of neutrons we have, then that means we have a difference of 3 neutrons. That's how many less neutrons uranium-235 has. Next one. So 14.6 question mark. Well, again, let's just look at this atomic number. 6 corresponds to carbon. Shorthand is just C. Pretty simple. And 14.7 question mark. What is this question mark? Well, again, let's just look at the bottom part. This corresponds to nitrogen, N. And notice how, can I change color? I can. Notice how they both have 14 on the top. That means the amount of protons and neutrons are equivalent. However, obviously, we don't have the same amount of protons, and that means we have different combinations of protons and neutron counts that account for these different elements and the different isotopes that we have. Next one. Oh, whoops. Next one is 131, 53, and 131, 54. Again, look at the bottom numbers. These are the atomic numbers. 53 corresponds to iodine, shorthand I. And this one, 54, corresponds to xenon, shorthand Xe. Pretty simple. Ooh, next one, 107, 47, question mark, and 109, 47. Now, notice how these two have the exact same atomic number. So that means it's going to be the same element. The only difference is the neutron count, which means we have different isotopes. So it's very similar to the first two examples we saw with the uraniums, where we have different amount of neutrons, exact same concept here. If we were to look at what this 47 corresponds to, we would figure out that this corresponds to Ag, silver. And you're wondering, well, how do we get Ag from silver? It's because when it comes to the periodic table, a lot of these names, most of them are derived from English names. So for example, carbon, C, nitrogen, N, obviously. However, some of them are derived from Greek and Latin names. So for example, Ag is actually derived from the Latin term Argentinium. Argentinium. Probably spelled that wrong. Spelling is not my strong suit. I apologize. And Argentinium basically means silver in Latin. And if you're wondering, well, Argentinium sounds quite familiar. Well, think about the country Argentina. For example, Messi. The reason why Argentina was named Argentina is because the Spaniards, they thought, oh, there's gonna be lots of silver in this land. So thus they named the land Argentinium after silver. So a little history there. Always fun to always have. All right, so then that's the first set of examples. Let's go on to the second set of examples I want to cover. That's going to be, once you get these slides, slide 17. So great. So our task here is to figure out whether it's ionic or covalent and to give the compound name. So let's just start with the very first one. So CF4, covalent or ionic? Well, if you look over here, carbon is a non-metal and fluorine is also a non-metal. When two non-metals join together, it's going to create a covalent compound. All right, so then we know that this is a covalent compound. Let's start naming this thing. The central atom is carbon. And then remember, when it comes to the central atom, we don't really put the prefix mono in front of the central carbon or central atom. However, we do need to put the prefix to indicate the number for the fluoride. So then because we have four of them, it's not quadro, like a quadrilateral, but it's tetra, Latin again. So this becomes carbon tetrafluoride. So then this is the name. Next one is CaCl2. Is this ionic or covalent? Well, we have a metal. Calcium is considered a metal. And then we have chloride, which is coming from chlorine, which is a non-metal. So a non-metal and a metal, this thing is ionic. All right, so then let's start naming this thing. Well, when it comes to ionic compounds, the cation just contains or remains the same, calcium. And then when it comes to the anion, we don't put the prefix at all. You just put chloride, because that is the anion form of the chlorine. Once you take away an electron, sorry, not take away, add an electron, it's an anion, so it's gaining electrons. So then this is the name, calcium chloride. We do not need to put in the prefix, like we don't have to say calcium dichloride, because if we know our ionic charges, we know that Ca is going to lose 2 electrons. So then we can automatically determine the fact that, well, we know chlorine's going to give up 1, or chlorine's going to gain 1, calcium will always give up 2. So then because we know that rule, that relationship, which is kind of fixed, we don't need to put any of those prefixes because that's redundant. We already know what's going to happen. That's why we don't need to add those prefixes. However, it's not always so clear with covalent compounds, which is why those prefixes do matter there. Next example, SO3. Well, again, let's figure out if this is ionic or covalent. We see that sulfur and oxygen are both nonmetals. So this is a covalent compound. So let's start naming this thing. Well, the central atom is just one of them, but we do not put mono. That is not for the central atom. That's only for the ligands or the things that bond to the central atom. So this is just sulfur. And then we have 3 oxygens. So then because of that, that becomes trioxide. Pretty simple. Nothing, no rocket science yet. We'll get there. 4, K2O. This is ionic. We know this is ionic because potassium is a metal, oxygen is obviously not. So metal and non-metal, that's ionic. So let's name this thing potassium. And remember, when it comes to ionic compounds, we never put the prefixes. Even though there is a K2, there's 2 of them. Don't put the prefixes. We don't do that with ionic compounds because, like I said before, ionic compounds have very strict the compound is going to be electrically neutral. So then because we know how much the anion will gain and how much the cation will give, those prefixes are not necessary because we know the relationship. It's a fixed relationship that we can figure out on our own. Oh, and I need to finish naming this thing. This is potassium oxide. Oxide for the oxygen, take out the suffix of oxygen, and then add the ide, oxide. 5, Mgi2. This looks like an S. Ionic, because magnesium is a metal, iodine is not. So let's name this thing. Magnesium, because Mg is magnesium, iodide. Iodide. No prefixes for ionic compounds, remember that? And iodide, we'll take iodine, get rid of the ene, and just add the ide. That's the prefix for anions. Next one, O2. Well, this is covalent because it's just made up of 2 oxygen molecules. They're both nonmetals. Yeah. And this is just going to become dioxygen because we have oxygen and then we have 2 of them. However, because oxygen is kind of one of those really common ones, if you just put oxygen, when people say oxygen, they mainly refer to O2, and it's fine if you put oxygen. I won't get mad at you. 7 is this one. All right, covalent, no, because aluminum is a metal and oxygen is not. So then this thing is ionic. So then if we start naming this, this becomes aluminum oxide. And it's funny because we have 2 suffixes or 2 subscripts over there, but we don't put any of the prefixes. So no dialuminium trioxide because of the fixed electrical relationships that we have. Aluminum will always give up 3, oxygen will always gain 2. Because of that fixed relationship, the prefixes are not necessary at all. Don't add them. Ionic compounds do not need them. Next one, BH2. This is ionic again because beryllium, Be, is a metal, hydrogen is not. So then we start naming beryllium. Oh, that's probably not how you spell it. You get the point. Hydride. Hydride is the anion for the H. 9. Okay, so 9 is a little tricky because arsenic is considered a metalloid, so it's not fully a metal. And here we get to the more technical definitions. And even then, it's not so clear because because when it comes to identifying covalent and ionic compounds, that's determined based on the difference of electronegativity. And for those of you wondering, the delta, which is this triangle, represents a difference. So the electronegativity difference between the arsenic and oxygen is going to tell us whether this thing is ionic or covalent. Problem is, once you take the actual electronegativity difference, we get a value of 1.7. Guess what? That's like on the cusp between ionic and covalent. So really, even with the electronegativity difference, it's kind of ambiguous. It's a little ambiguous, which is why for this case, you can kind of go for both. So if you want to say, oh, this is a covalent compound, well, then it will have to be diarsenic trioxide. I've seen online this form. And if you want to say, well, 1.7, we gotta make an ionic compound. Sure. That becomes arsenic 3. The reason why I need to put the 3 is because arsenic can have multiple charges. So in this case, it's going to have 3 oxide. Both work. I've seen both online. And if you just actually look at arsenic trioxide or diarsenic trioxide, arsenic 3 oxide, it's actually a mix between covalent and ionic bonds. So that's why the very last one, this As2O3 is a little ambiguous. So a little tricky on the tricky end. So that's that example. And then for the very last examples, so that goes, once you get these slides, slide 21, practice 1. So naming these compounds. So more naming compound practices. So MgBr2. Well, this is an ionic compound. Mg is a metal, beryllium is not, sorry, bromine is not. So then this becomes magnesium bromide. Oh, I should probably separate those two because those are two separate words. All right, next one is this. So this is an ionic compound because we have the zinc and then we have the polyatomic ion of cyanide. So then because of that, there's going to be no prefixes. So this becomes zinc cyanide. The Cn is a polyatomic ion. Try to commit that into memory or put that in the cheat sheet. Me personally, I'm most likely going to put that in my cheat sheet. Yeah. CrF3. Well, this is chromium and fluorine, metal, non-metal. That's going to be ionic. So this becomes, oh, and for this one, because chromium is a transition metal, we need to specify the charge it has because chromium can have multiple charges. I forget, I believe one of them is +2, but in this case, we have +3. And we designate that with Roman numerals. For example, chromium, parentheses, 1, 2, 3, for the +3 charge. Oh, I spelled that very wrong. Fluoride. Remember, no prefixes. This is an ionic compound. Fluoride. There we go. Next example. Thank you. Next. Next example is SNO. All right. So for this one, we have SN, which is tin. So SN is tin, which is a metal, and oxygen is non-metal. So then because of that, this is an ionic compound. This becomes tin, and we need to specify the charge because it is another transition metal, tin 2 oxide. 2 representing the +2 charge. And then those +2 charges, they gave up their electrons to satisfy the 2 electrons that oxygen needs to be happy. Next example, HClO4. This, if you remember from the last slide, I believe it was the very last slide. Yeah. This is a strong acid. So I would just commit this to memory if I were to you. This is perchloric acid. Strong acid, remember, you do not want to be touching this stuff because it will burn right through your skin. Never fun. And that trip to the hospital would not be fun either. Expensive too. HF. Well, if we go back to the naming schematic, if we have an HX, HX being an halogen group, so for example, fluorine, chlorine, fluorine, which we have, it's going to be the hydro, this in parentheses is going to be the halogen prefix. Acid. Oh, sorry. I need to add the ick. Not ick as in like, oh, that's my ick, but like the ick at the very end. Ick. Sorry. Acid. So in this case, we have a fluorine over here. That halogen prefix is going to be fluoro. or fluoric. Fluoric? Wait, fluoric. Hydro. Wait, hold on. Let me double check my hydrofluoric. Fluoro. Fluorine is such a weird. I can never spell. Fluoro. That's going to be the prefix. So then because of that, this becomes hydrofluoric acid. All right. And then the next one, is going to be HCl. This is going to follow the exact same schematic as example F. This becomes, and this is another strong acid, so I will commit this to memory if I were you. Hydrofluoric acid. All right. All right, so then those are pretty much all the examples I have for naming. We did the isotopes. There is one more thing I do want to show, and those are stuff with sig figs. So then in class or in the session, hopefully Drew and I will go over the very last slide, which is the demonstration with the sig figs and the ruler. Guess what? You're not going to be dealing with a lot of rulers in chemistry. So I do want to give a more relevant example, one with a beaker, because you will be dealing with a lot of beakers. So if I were to draw a little bit of a beaker, so then this is 40, this is 35, everything's going to be in mLs. Because we're, and then 1, 2, 3, 4. 1, oh, that's crooked. Crooked. Embarrassing. 1, 2, 3. Guys, this is the best I'm gonna do. I'm sorry. I should do better than this. And then I will draw a little bit of water. Let me do this in blue actually. Ooh. Because I am not a black hole. Look at me adding a little color to this presentation. Then I start coloring things in. And the blue represents water, obviously. And let's just say I have this Buret reading. And I ask you, what's the measurement of this thing? Okay, well, from here, we can automatically determine this is going to be 36. So 36 ml is what I can definitively tell you. However, that's not good enough because when it comes to measuring devices, we need to have 1 degree of uncertainty, which means we have this part over here. Let me do this in red actually. So it's a little more obvious. We have this part over here. However, we see that this meniscus, remember, when it comes to water, it's always going to have a bit of a divot in glass. That's just the way that water behaves because of the adhesion forces are stronger than the cohesive forces. If you're taking AP chemistry right now, you're going to learn what that is later. It's not important for now. But just know that's going to have a little bit of meniscus, a little bit of a dip. And we see where that dip is. We see is in between this 36 mark and 37 mark. So then because of that, I will estimate that to be around the half mark between 36 and 37. So really, if I want to report the number, I will report the number of 36.5 milliliters instead of the 36. Because the 36, I have 2 exact significant figures. Those are the numbers that I do know for sure, no doubt about it. But the 0.5, I'm not too sure if it's 0.5. It could be 0.4. It could be 0.6. It could be 0.3. I don't know. I'm just inferring that number based on what I see. But for now, I think 0.5 is a very safe bet. So then that's the more relevant example I want to show as sig figs. And that's it for this session. Thank you for watching. And Hufflepuffs are cool. And for those of you wondering who said Hufflepuffs are the leftovers or they're not cool, you know who you are. I won't be name dropping, but you know who you are. Till next time.